Okay, everyone, welcome to class 6 in Physics 203. This is a class on blackbody radiation, which we've already talked about a couple of times and done one sample problem on, the radiation from the sun. And this was a key component to the, again, the transition from classical to quantum physics, one of the very most crucial experiments that led people to believe that light itself, in fact, came in packets and quanta or quantized energy as opposed to a continuous range as in classical physics. So we actually experience blackbody radiation or thermal radiation, as it's sometimes called, in our everyday lives. So here's an example of, well, you might not see this every day, but you could, it's still, you could drive to a plant and see it. This is an example of molten steel glowing at around 1650 Kelvin, approximately. And as you heat up steel, it gradually glows red and orange and yellow and eventually white, and this is kind of a yellow-white color. So this is thermal radiation coming in the visible part of the spectrum, coming from an everyday object or at least a naturally occurring object, molten steel. And then at much lower temperatures, we get, as we'll see when we look at the blackbody curves versus wavelength in a second, we get different types of radiation. So this is obviously a picture of a house. It's a false color image of a house. When you look at a house, it doesn't really look like this, especially at night. But this shows the infrared radiation or infrared light coming from different parts of the house. And more energetic light, that is light with smaller wavelength or higher frequency, is shown in yellows and reds. So you can see the heat, which the higher temperatures around the windows and the attic and the door where the heat is escaping. And companies use this to help diagnose heating and insulation problems in houses. So that's at approximately 285 kelvins. Okay, so and we radiate as thermal bodies too. We radiate at approximately the same temperature as the house. So you can have thermal images of people. But going back to the 1900s, or going back to the issue when it was studied in the 1900s, black bodies, as we touched on before in a previous video, are an ideal absorbers and emitters. Okay, so all objects in thermal equilibrium absorb and emit radiation in a balance. If you're sitting there, you're taking light and other forms of electromagnetic radiation in, but your body is also radiating it back out, and because your temperature stays constant, you're not taking in more energy than you give out. A black body, what makes something a black body is it takes in, it absorbs rather than, most of us reflect some of the light that comes to us. That's why we see colors on our clothes and so forth. But a black body absorbs absolutely all the radiation that comes into it. And it's an ideal black body is often represented by this box where we have a small hole here. And so any radiation which comes in and passes through this hole is emitted and bounces around and equilibrates with the atoms in the walls of the cavity, and then just basically just sort of is slowly, very slowly emitted back out of the cavity in a very characteristic form called the blackbody spectrum. And speaking of which, these are blackbody spectrums. So black bodies, as I said, and non-ideal everyday objects like molten steel or a house, just a little less efficiently, emit over a range of wavelengths. So this on the horizontal axis is wavelength, increasing to the right. On the vertical axis is the intensity of the radiation, and that is the amount of energy at that near that particular wavelength. And the peak of the curve depends on temperature. So you can see we don't have room temperature, 300 kelvins here. That would be way over here. We do have 900 kelvins. And you can see that most of the light or radiation intensity at 900 kelvins is in the thousands of nanometers, which is in the infrared. So you can imagine for 300 or 285 kelvins, the house is going to be way out here. So it's all infrared radiation, which is why we can't see it invisible at night, but we can see it with an infrared camera. On the other hand, the the molten steel was at I think 1650 Kelvin, somewhere between these two curves, and so the principal the maximum radiation is still in the near infrared around 2000 nanometers, but there's a good bit of intensity in the visible spectrum, which would be right here between 400 and 700 nanometers, which is why we see that molten steel as yellow and white, okay, because it has yellow is on the high energy end of the spectrum. Okay, so and I should say, just in terms of units, this vertical axis, our intensity on this graph is measured in units of power per unit area, or the relative intensity is measured in power per unit area. Power per unit area is intensity per unit wavelength. Okay, so the units would be joules per meter squared per meter, since wavelength has meter, or joules per meter cubed. And that's so that the total amount, if we integrate this curve, as we'll talk about in a second, with respect to the wavelength, we get the total power. So if this is the power per unit wavelength, then if we integrate with respect to wavelength, we multiply by wavelength, we get the total power. So the area under this curve is the total power per unit area emitted at a given temperature by an object. Okay, so two key properties of blackbody intensity curves. So here are those curves again. The first one you might have already noticed, we already kind of commented on, and that is the peak wavelength, the wavelength at which the blackbody reaches its max, at the wavelength at which the maximum radiation is occurring, gets smaller. The wavelength gets smaller as the temperature of the blackbody increases. So at 900 it's here, 1200 it's here, 1500 it's here, 1800. So you can see it getting gradually smaller. And that makes sense because smaller wavelengths correspond to more energetic light. Infrared light out here at 1,000 nanometers is thousands of nanometers is less energetic than visible light here at a few hundred nanometers, and which is less energetic than ultraviolet light here around a couple hundred nanometers. So as the temperature goes up, the peak wavelength gets smaller and smaller, corresponding to more and more energy in the most concentrated region. And this is expressed in Wien's law. This is Wilhelm Wien, who played a role in the early development of thermodynamics. And it says that lambda max times T, the temperature, is equal to this constant. And he just found this empirically by looking at these curves and noticing that if we multiplied the maximum wavelength times the temperature in kelvins, we always got a constant, which has units of meters times kelvins, right? Wavelength times temperature. So this is Wien's law, and which expresses this movement of the peak backward toward lower wavelengths, shorter wavelengths as temperature increases. The other important law is that I already said that the total power emitted, or I should say the power per unit area, which is called the intensity, is the area under the curves that increases rapidly with temperature. And we can see this visually. So if we look at the area under the curve, for 900, it's a little bit. For 1200, it's bigger at every point, and it grows quite rapidly. So if we double from 900 to 1800, we can see that we've way more than doubled the amount of area under the curve. And so this is expressed in the Stefan-Boltzmann law. Josef Stefan here was the advisor of Boltzmann, who was a very important thermal physicist. Both of them were, but Boltzmann is probably the most famous thermal physicist. And this is expressed in the Stefan-Boltzmann law, that the power per unit area is equal to this script, I'll call it epsilon, times sigma times t to the fourth. And sigma is the Stefan-Boltzmann constant. We've looked at it before. It's 5.67 times 10 to the minus 8 is the magnitude of it. And the power emitted goes as the temperature to the fourth power. So if we double from 900 to 1800, we double the temperature, then the temperature goes up by a factor of 2. The total power would go up by a factor of 2 to the fourth, or 16. So there's 16 times as much area under this curve as there is under this curve. And what about this epsilon? This is called the emissivity, which is 1 for an ideal blackbody, because the blackbody is an ideal absorber and emitter, and less than 1 for everyday objects, okay, because everyday objects don't radiate from all of their internal energy. Like your body holds some of the energy inside, and chemical energy and vibration and heat energy, and it's only the energy at the surface that the vibrations of the atom at the surface that contribute. So the emissivity is 1 for a black body and less than 1 for other objects. Okay, so what about classical physics? How did it do on trying to make sense of these curves? So classical physics views the contents of a blackbody cavity as electromagnetic standing waves, also known as EM, or electromagnetic modes. And here's a picture of a blackbody cavity with a mode in it, where these are the, I believe, the electric fields. So there's a certain pattern to it, kind of like a standing wave on a string, but in 3 dimensions. And according to thermodynamics, though, each of these standing waves has a certain amount of thermal energy, kBT, associated with it. This is something called associated with something called the equipartition theorem. So you can, equipartition theorem, you can Google that if you want, which says that each degree of freedom has 1/2 kBT of classical energy, thermal energy associated with it. And each standing wave here has 2 degrees of freedom, because the electric field can point either up and down or left and right. So this is a sample standing wave. So at long wavelengths, okay, so like this wavelength is pretty long because it doesn't go through many oscillations. There are fairly few possible modes, but as the wavelength gets smaller and smaller, okay, so as these oscillations got more and more, there there turns out there's an explosion of possible ways that these standing waves can fit inside the cavity. Okay, so you could have like 1 million oscillations this way, and 2 million this way, and 3 million this way, or 3 million and 1 this way, or 2 million and 1 this way. So the number of modes just starts to explode as the standing waves fit in the cavity, and each standing wave, each of these many standing waves has a thermal energy kBT associated with it. So this leads the energy intensity to blow up at small wavelengths classically, okay, because we multiply this huge number of modes at small wavelength times each mode gets the same amount of energy kBT. And we can see that this is the curve we get. This is the experimental data. Okay, so as we go to smaller wavelength, it hits this peak, as we've seen, and drops down, back down to 0. But the classical prediction, which is called the Rayleigh-Jeans formula, as I'll show you Rayleigh and Jeans in a second, blows up. So it starts off matching at long wavelength pretty well, because there are a few modes, so it matches up at long wavelength pretty well, but then it departs or diverges from the experimental data and eventually just blows up here and does not match the experimental data. So the history of this formula briefly, Lord Rayleigh, who was a famous British physicist, found in 1900 that the intensity should go as 1 over lambda to the 4th power. So this is a 1 over lambda to the 4th dependence. And then a few years later, James Jeans partnered up with Lord Rayleigh and found this proportionality factor, which turned out to be 2 pi c times kBT, which is definitely the first thing that I would have guessed. No. But anyway, this is the proportionality factor, and this is called the Rayleigh-Jeans formula. But clearly, its prediction doesn't match up with the experimental data. So something is going on here that classical physics can't explain. Okay, so this brings us to the work of Max Planck. Max Planck, this is a picture of a young Max Planck. Often you see older pictures, but back in his earlier days, in the 1880s, he was a fairly conservative physicist. In fact, he was not convinced of the atomic theory and very much believed strongly in classical and thermodynamics concepts. But he saw this in the 1880s and 1890s as these blackbody radiation curves came out. He searched for a way to match them, to come up with a theory that matched them. And classically, he thought that they should be classically explained. So he tried out lots of different mathematical expressions and lots of different theories, which I won't go into great detail. But finally, he hit, more or less by trial and error, on a complicated formula in 1900, which could reproduce the curves. And this is the formula. This is the intensity, the power per unit area per unit wavelength, is equal to this business, 2 pi c squared h, where h is a new constant, times 1 over lambda to the 5th instead of lambda to the 4th, times this exponential factor here. So you can see he had to do probably a lot of trial and error to come up with this formula, which fits here. But we can see that that sort of why it goes to 0 at low wavelengths. If this lambda to the, these are all constants, this 1 over lambda to the 5th term blows up very fast. But here, as lambda gets small, we have e to the a constant over a very small number, which would be a very, very large number. So e to the very, very large number. And the exponential function grows really, really fast. Okay, so we have a very large number in the denominator here as lambda goes to 0. And so even though this is diverging, the exponential is is blowing up faster than this term is diverging, and so we get down to 0. So matching those curves. So Planck could derive this formula only if he assumed, so he wanted to derive them classically, this formula classically, only if he assumed that the walls of the cavity were made of atomic oscillators, okay, as suggested by this picture. So these are, so there would be an atom here and it would oscillate and put out a wave of a certain frequency, and another one would be oscillating faster and put out a wave of a slightly lower frequency, and here's one putting out a strong wave at a much lower frequency, and so forth. So these are atomic oscillators, and he had to assume that they absorb, in order to get this formula, he had to assume they absorbed, that the oscillators absorbed and emitted radiation in discrete amounts of energy, delta E equals HF, where H again is a very small constant and F is the frequency of the light. Okay. Now, as I said, Planck was a conservative physicist. He tried to make his formula work. He hoped he could fiddle with it and make it work as this constant H would go to 0, and it's possible to show mathematically that as H goes to 0, you recover classical physics. Certainly, it means that you can have any value of energy, since energy is not coming in packets here. If H goes to 0, it can come in any amount. But this should say was not able to do so. So Planck was not able to do so. He tried to make his formula work. So this constant H became known as Planck's constant, and it has this value here, 6.626 times 10 to the minus 34 joule second. So it's very small, but not 0. Okay? And remember we talked about these properties of Blackbody radiation spectrum, Wien's law and the Stefan Boltzmann law, which had been determined by experiment beforehand. It turns out that those, with a little work, these can be derived from Planck's Blackbody radiation law here. And I'm not going to do that here, but you can see examples in our textbook if you'd like to see the derivations. Essentially, to get the maximum wavelength, you would take the derivative of this expression and set it equal to 0 to find the maximum of the intensity. But it's a big derivative, so it's a involved calculation. And to get this, you would integrate this intensity with respect to wavelength, which again is a rather challenging integral. But you can look at those in the textbook if you like. But the point is that Planck's formula not only matched the curves, but it reproduced Wien's law and the Stefan Boltzmann law. So Planck maintained his view that the atoms in the walls of the cavity could just vibrate at certain allowed frequencies, forcing the light energy to take on quantized values. But it was the atomic oscillators that were quantized, and the light itself, the light energy, could in principle take on any value, but it was just being forced to take on these values in units of HF by the behavior of the atomic oscillators. Einstein came along and proposed that light itself carried its energy in the form of packets called photons. He proposed this in the neighborhood of 1905. And this is our modern interpretation of the Blackbody effect, that it's not just that the atoms in the walls of the cavity could vibrate only at certain allowed frequencies, but that the light itself comes in discrete packets or little energy packets, or like we think of them as little balls called photons, where E is equal to H times F. Okay, so we had that formula. Sorry, E is equal to h times F is the energy of the photon. And here's a little cartoon here, just for fun. A photon checks into a hotel and is asked if he needs any help with his luggage, and he says, "No, I'm traveling light." Okay, so so photons, these little balls of energy, are the way light travels or carries its energy, like in his little suitcase here would be the energy. So the ultraviolet catastrophe is avoided, as there's the ultraviolet catastrophe being the mismatch between the classical spectrum, which diverges, and the experimental data, which comes down to 0 at low wavelength, basically because there's just not enough thermal energy around to excite very high energy photons. Okay, so this goes a little more into the theory of this, but and thermal physics, but the probability of creating a photon like a gamma ray, which would be way down here, is if it's a discrete amount of energy, is very small. Okay, and so we get around that, and so this disagreement. So overall, just to summarize, blackbody radiation and thermal radiation is all around us. Every object is radiating thermal energy, electromagnetic energy proportional to its temperature. The blackbody radiation curves, as showed here, didn't agree with the predictions of classical physics, specifically electromagnetism and thermal physics, which would put together, said that this should blow up. And Planck came along and found this formula, which fit these curves and reproduced these empirical formulas, Wien's law and the Stefan Boltzmann law. And then Einstein said, well, actually, it's light itself, not just the atoms in the walls, which are quantized. Okay, and so this was a key experiment, as I mentioned, blackbody radiation, a key experiment to the idea that things were quantized, that the energy of light is quantized into these packets called protons. Okay, thank you for your attention. And I will see you in class. Next time we'll look at another interesting experiment called the photoelectric effect.